Welcome to the fifth session of this Golang playlist. So today we'll be talking about understanding floats and complex numbers. So our summary guide will be float numbers, complex numbers, and code illustration. Floating point numbers have integer values as decimal points and a fraction. A float can store fractional numbers or decimal, unlike the int data type. Like many modern languages, Go uses the IEEE 754 standard to implement float. Storage of float is divided into three values. So the first part, a single bit is used to store the sign value, few bits are used to store the integer value, and the rest are used to store the fraction. Floats have limited value of precision to a certain extent and should be used carefully. When comparing floats, they should not be compared directly, but instead, the check should be around the difference between a given range, more like a delta. We have this table that shows a brief summary of the type, the description, and the range of values for the float 32 and the float 64. This table shows the the range. So the way I did it here is that for the float 32, there's something we call the minimum subnormal and the normalized. And what I mean by that is that normalized numbers, their scientific notation with the decimal always shifted so the first digit isn't zero. While subnormals, they are so tiny that they can't fit into the normal scientific notation rule. So we relax it and let them start with 0.00. So that's why for the minimum, you'll be seeing two values. That's the subnormal and the normalized. And for the float 32, I'm limiting them to 9 places, 9 DPs, that's 9 decimal places. While for the float 64, I increased it to about 15 or 16 decimal places. Any which way, you can see these constants in Go using the math package. So we have the math.max float 32, we have the math.smallest non-zero float 32. So and we also have equivalent for that for the 60 float 64 as well. Float 32 uses 32 bits of memory to store values, while float 64 uses 64 bits of memory. Though in Go, the default is float 64, regardless of architecture. That's 32-bit, 64-bit, ARM, x86, whatever. So Go basically says you get 64 bits unless you ask for less. But it's good to know that a 32-bit system can still work with 64-bit values. That's both integers and float, but it doesn't handle them as naturally as a 64-bit system would do. So here's what happens under the hood. On 32-bit system, CPU registers and memory address are 32-bit wide. So if we want to store a float 64 or an int 64, the compiler has to split it across two 32-bit registers or memory address. So this means arithmetic or logic with 64-bit values often requires multiple instructions instead of one. Hence, we can infer that it's supported but just slower. Now we'll talk about the data type complex. Complex numbers in Go have the real and imaginary parts represented by float. So one of the reasons why I had to match them together is because they are intertwined. Complex 64 uses float 32 for both the real and imaginary parts, while complex 128 uses float 64 as the real and imaginary parts each. For the complex data type, we have the built-in function complex, which can be used to create a complex number. We also have built-in functions, the real and the image function notation, which can be used to get the real and the imaginary part. So this table just shows a mental map of the type, the description of complex 64, which is set of all complex number with float, real and imaginary parts, and also the equivalent for complex 128. Before we go to the code illustration part, there are some things we need to know. We should be careful when using float for monetary values. We should even try as much as possible to not use it. And also, when comparing floats, instead of comparing floats directly, we should use more like a delta, that's a change between two values, and see if the difference between the two floats is greater than or within the range we have specified. Then we can consider that it's equal or not. If ever we want to work with monetary values, we should use the int64, and also we should store the integers of the currency in the base currency value, for example, Nigerian kobo, cents, then shillings, because this gives for faster calculation. Ints are usually very fast as compared to using values like floats. Hi, welcome to the coding session for this float and complex data type. So I'll be starting with float here. So let me make my comment here. So the first thing, let's try to create a float variable. So small float 32, and it will be in the type of float 32. So basically we can make a variable of the float type with the float 32 and the float 64 respectively. So if we have this, it equals to, let me use number like 45.67389762 yeah. So then I'll try to print it out to the console. fmt.println with the small float value. So when I run main.go, yes, so we have 45.673897. So actually the way float 32 works, it's not as precise as the way float 64 works. So I purposely added more than enough number here because I know maybe around 60 p's or so, that's where the precision value stops. So if I count this, that's 1 2 3 4 5 6 7 8 9, but here we are having 1 2 3 4 5 6. So it's about point is about 6 decimal place in terms of precision. And let's say we have another one, var big floats, let's say 64, with the type as float 64. Now we assign it as a number. Let's use 92.873262914325676. Let's see, fmt.println with the big floats. So let's run this on our console and see what will be outputted. So okay, we have a wider range of in terms of precision here. So this is 1 2 3 4 5 6 7 8 9 10 11 12 13 14. So it gives about a precision of point that's in 14 decimal places after the decimal point here, which shows that it is even much more precise. And recall, so I commented out the code for the previous ones here. There's something we can use in Go to get the values, the range of values for a float 32 and a float 64. So I'll just it's in the math package. So we have fmt.println, we have the math.max,
But before that, let's check for the minimum value first. So we have this, then I'm going to duplicate that, then this will be for small for 64. Then I want to have a divider in between, so we have a clear cut distinction. Then we have another which is fmt.println math dot math.max float 32. Then duplicate this as well, this will be 64. So this is for the smallest number possible as a float. This is for float 32. Then this is for the smallest number possible for float 64, while these two below are for the numbers, the highest number that can be saved as a float 64. So I'll run this code now. That's go run main.go. So just like we had in the previous session, 1.401 some numbers raised to power minus 45. Then we have the that of the float 64. So we have that of the float 64, which is this. Then we after that we have that of float 32. So this is the highest number possible for it, and for this we have the highest number possible for the float 64 as this. So to work with complex values, let me have a comment here. So complex values are when you split up a complex value, in the composition we use float values to actually create them. So if I have something like my real part, then my imaginary part, and let's say they are float 32. Now I'm disabling this extra 5 minutes. So we have two float 32 values. So how do I make them a complex number? So var my complex, which will be my complex 64, will be equals to, we use the inbuilt complex function for complex. Then we have my real part and my imaginary part. So if I have this fmt.println my complex 64, let's see what will be printed to the console. So yes, the reason why we're having 0 and 0 is because remember the base value for all numbers is 0. That's why it's like this. So even irrespective that we're working with float, it still respects that numerical law in Golang that says all numbers, all numbers actually has a all numbers actually has the base value as 0 if nothing is being stated there. So let's say I do something like this. My imaginary part equals to 5, while my real part, let's say we say it's 10. We'll see the values that will be printed will actually be different. So that's just how complex value work. And since we are working with float 32 here, and if we check the type of this, it will be complex 64, because just look at it in terms of composition. We have a float 32 and a float 32. So when you just do a bit of math, it becomes, yeah, this complex 64. So if we are to do for complex 128, that means we'll be needing to add two float 64 values. So I want to reuse this values here. So var my real part and let's say my imaginary part. Okay, we can still leave it. Just think of something. My real part 64 and my imaginary part 64, and each of them are both floats 64. So now let's do the assignment. My real part 64, let's say 224, and my imaginary part 64, let's say 10 here. So var my complex 128 will be equals to using the inbuilt function complex, and we just put in our my real part and my imaginary part 64. I think I'm missing something here. Then let's print it out to the console. So my complex 128. So if we do go run main.go, we can see we have, so each of these thing that is being outputted to the console, so this is complex 64 while this one will be complex 128. Naturally in Golang, use of complex numbers is not really used, but in cases where you find them, this can be an helpful guide to just learn about the basics about it. Don't forget to like and subscribe.